At the end of the previous section, we looked at a European-wide projection. We're now going to look at, we're going to go back to a more global system that will then lead us on to a much more local system for Sweden. And to do that, we're going to look at this Mercator again, the tube that's been rolled up. So when we looked at it previously, with this massive distortion of Greenland and Antarctica, we had the tube rolled up like this, standing up, so to speak, and the Earth pushed into it. And we have this line where the tube is touching the Earth around the equator. But if we look at the Earth, now this line where it touches is the least distortion. The farther away from this touching line that we get, the more distorted our map is. And when we think about the Earth, most countries are actually sort of long, continents are long, and a lot of countries, or many countries at least, are quite long from north to south, rather than being broad from east to west. That's not always true, not of every country, but there's a general tendency for the continents at least to look like that. Sweden looks like that. Other countries, Italy, the UK, kind of drawn out. So this means that really that's not ideal in that sense, to have the minimum distortion spread along a line going this way, and then the farther out you get north and south, the greater the distortion. If instead we turn it around, then we have minimum distortion going all the way along this line, and then the maximum distortion coming out here. But because our continents also follow this line, if we rotate the ball of the Earth around, it means that we have this best fit can cover a larger portion of the continent or landmass in question. This has been used, this system has been applied to the entire globe because we have this kind of general pattern of being stretched out north to south. Obviously it's not true everywhere, but it's sort of true to a certain degree. And better this way than around the other way, slightly. And this was defined in a sort of somewhere around either during or shortly after the Second World War. The American military came up with this idea of the Universal Transformer Mercator, UTM. And this is a way of projecting from the globe using standard meridians, standard lines where the paper touches. So the equator goes around that way and a meridian goes around the other way, and we're using standard meridians for where we let the paper touch the Earth. We can then define a series, a whole suite of map projections. Each of these is a different one. In reality, the globe is touching the same line all through along this way. It's just been chopped up into these pieces to make it more convenient for producing maps, but actually it's strips going down like this for our projection, using this central meridian. This method of projection can be applied to any model of the Earth. So you could use RT90, you could use WGS84, GRS80, you can use anything you like, SWEREF99, all of these, and use the same method of projection going from whatever model of the Earth you're using up to a flat surface. So UTM can be applied, so you need to supply the information about which UTM bit of map you're using and from which model of the Earth it was taken. Both parts are needed. So if we look at Sweden, moving in closer to Sweden, we can see that we can apply this UTM system over the whole globe, and we end up with, when we look at Sweden, being covered by several bits of the UTM system. As I said, we can really regard the columns as being one and the same thing. They get these letters telling you how far north you are or how far south you are. But actually, it's the number, the 33, that's important here, and the 32 gets us in on the west coast there, and the 34 here, and that's a tiny little bit on 35 there. But generally speaking, 33, 34 are the main zones covering Sweden, with a little bit of 32 there. So that's in our UTM system. When we look at Norway, Norway somehow has managed to get 32 stretched out to cover a bit more than normal. I think probably because that line would be just annoying or something. I'm not sure how they got away with that, but that's just standard. That's how it works. So congratulations, Norway. Whereas nobody else has been given that privilege. There are a couple of other exceptions around the globe, but generally speaking, it just follows this regular grid, where Sweden lies in this 33 and 34 zone, with a little bit of extra around it. So how do we go from that to this thing that I've been talking about, this SWEREF99 TM? So SWEREF99 is this the ball, a spherical model of the Earth, or an elliptical model of the Earth, oblate spheroid, defined by the rotation of satellites around the Earth, with some other adjustments so that it's we're connected to Europe as the tectonic plates move apart. We need to make sure that we stay within Europe rather than drifting off somewhere else. Centimeters per year. So it's this model of the Earth using the satellite's rotation connected to Europe, and that defines SWEREF99. And then the TM tells us that we've taken that transverse Mercator or transform Mercator projection way of doing things, and we're going to apply it to Sweden. So we take our UTM zone 33, and as we saw in a previous slide, Sweden was covered by zone 33, 34, a bit of 32, and a tiny bit of 35. Well, we just say, nah, you know what? We'll use 33 over the whole of Sweden. We'll take zone 33 on SWEREF99, and we'll just say that it applies to the whole of what would normally be covered by 34 and what would be covered by 32, but we'll say, forget those, we'll use 33, which means that the distortions are going to be larger out towards those edges in zone 34 and 32 than they are in 33, and as they would be otherwise. But you know what? It's not enough to worry about. Not for what we're going to use SWEREF99 TM for. You know, if you want to get an ambulance to an injured person, you don't need millimeter accuracy. You know, it's good enough with meter accuracy. And in actual fact, in most cases, you're going to be a lot better than that. So it's good enough for what we want to do. As long as you're not using SWEREF99 TM in an inappropriate manner to do something that requires much higher accuracy. So SWEREF99 TM, good enough for making maps, covering the whole country, for getting from A to B, doing that sort of thing, great. And that's the national grid. And it replaced the previous system, which was based on the RT90 model of the Earth, which was conveniently called RT90 2.5 new degrees west. West of Stockholm Observatory, which was then defined as being a particular distance from Greenwich in itself. Yeah, lots of things shifting backwards and forwards there. It was a fine system. It was locally defined for Sweden and was great, and in some respects was actually more accurate than this, but not terribly convenient, given that we now have satellites and GPS and all that sort of thing. There was no proper direct connection. It's been abandoned, but you will find data, less and less so, but you will still find data in the RT90 system and in this RT90 2.5 new degrees west. So you need to be aware of it. This, at least in Sweden, you will find this data. There are a whole suite of projections connected to both RT90 and SWEREF99 TM, SWEREF99, sorry, that we will come on to in a second. Because you don't have to just follow the central meridian for the 33 zone, or this 2.5 degrees, new degrees west of Stockholm's observatory. You can actually move your center of projection, your meridian, to different places to provide a more accurate, fewer distortions locally to where's relevant for you. You can move that line of tangent around. And this is what we equally done in SWEREF99. I'm not going to talk about that anymore for this, but for RT90, but for SWEREF99, we have this system where we have the model of the Earth, the round model in longitude and latitude, so we have degrees, that's longitude and latitude, and then we had our central projection covering the whole country, which went up here. That we call TM when we stretched it out to cover the entire country. But when we move the line, when we move the tube, the piece of paper around a little bit, one way or another, we can get a more locally accurate projection, so that when we are actually interested in millimeters rather than just say half a meter or a decimeter, then we can use one of these. There are another couple of small differences as well in how the projection is played out, the scaling factors mostly. But these then are, rather than being called SWEREF99 TM, they're called SWEREF99 18 or whatever your meridian is that you're using. So you've got these projections locally that are more accurate for detailed work. And for those of you who are going to stay in the Gävle area, you can see that working across borders between two different communes, it could provide you with a problem if you're working in different coordinate systems. You will need to cooperate and transform your data from one to the other. And that's relatively straightforward. You're both in a SWEREF99 system, so it's reasonably simple, but it still will require a transformation. We'll get onto that shortly.